Arjan, thank you very much. And actually, you pronounced correctly Zacharias, so that's great. Uh, anyway, yeah, so I'm Mario Zacharias. I'm a Marie Curie postdoctoral fellow at INSAREN in France. And today I'm going to talk how we can perform a harmonic lattice dynamics and electron-phonon calculations in a very simple and efficient way. So basically, I will talk about the special displacement method, which is a non-perturbative approach, supercell approach, where you can actually use this methodology to incorporate anharmonic lattice dynamics and electron-phonon coupling in a very simple manner, actually. So here is a photo from the group in Rennes that I'm currently located. And these are my supervisors, Jack Ivan and Claudine Catan. And in this group, they have a high activity, theoretical activity for perovskite physics. And it's actually a great platform for me to do my Marie Curie fellowship, where I'm actually applying these state-of-the-art methodologies for computing anharmonicity and electron-phonon coupling effects in perovskites. And here is another photo from the APW school in 2022 in Austin. And in this school, you can learn actually about how you can perform first visible calculations of electron-phonon coupling, either perturbatively or non-perturbatively. And I'm inviting you also to check the upcoming APW in-person school in 2024 if you are interested. So here's a short summary of the lecture I'm going to give today. So firstly, I will talk about the non-perturbative approaches to electron-phonon coupling and then I will discuss how these approaches can be taken from the stochastic framework to the deterministic framework. And then I will gradually introduce the special displacement method, discuss the theory of the methodology, its physical interpretation, and some of its applications. At the last part of my talk, I will discuss how we can upgrade this methodology and account for anharmonic lattice dynamics. And finally, I will present an example about computing anharmonic electron-phonon coupling in perovskites. So there are several codes in the literature for computing temperature-dependent properties from first principles. So these codes, they either use perturbative approaches or non-perturbative approaches. So the state-of-the-art codes for perturbative approaches is the electron-phonon, the EPW, electron-phonon code of Feliciano Giustino, or the ab-initio code of Xavier Gonce, where the electron-phonon matrix elements are calculated from density functional perturbation theory within a single unit cell. So other codes like VASP or the ZG module in EPW, which I'm going to talk today, or IPI or FHI aims, they displace the nuclei in large supercells, and the electron-phonon matrix elements are not evaluated explicitly. So today I'm going to discuss how we can displace the nuclei in an optimized way in large supercells to incorporate efficiently the effect of electron-phonon coupling and at the same time capture anharmonicity. So here is the expression actually that we are implementing in order to obtain the special displacements, which I call also ZG displacements after Zacharias and Giustino. So here are the displacements of a nuclei K in a unit cell P, which is written as a linear combination of the phonon polarization vectors with coefficients determined by the mean square displacement of the atoms along a particular phonon mode at temperature T. So these mean square displacements depend actually on the Bose-Einstein incubation factor, and this is how the temperature enters in these displacements. And these displacements are also scaled by the phonon frequency of a phonon with wave vector Q and phonon branch index nu. So here, what we have the freedom to do is to choose the signs of this expression in order to optimize our displacements and eliminate the non-perturbative error in our supercell calculations. So this code, the ZG.X code in the APW module, will just determine these signs in a way so that the non-perturbative error is minimized. And this is implemented in the quantum espresso and VASP as well. So in a snapshot, the special displacement method is that we start from the high symmetry configuration with the atoms at static equilibrium. Here I use the example of the high symmetry cesium lead bromide with all octahedra aligned. And then after we calculate the phonon frequencies and the phonon polarization vectors, we can generate a thermally displaced configuration in an optimized way so we can evaluate temperature-dependent properties. So why is this methodology useful compared to perturbative approaches? You know, sometimes when you do perturbation theory, it might involve some very complex theory, and even the implementation in a code, it might be even more complex. And then if you have also anharmonicity in the potential energy surface, might be even more difficult to do the theory and also the implementation. you need to evaluate the electron-phonon matrix elements explicitly, and sometimes it might require some linear interpolation to go to very fine Q grids. And also in perturbation theory, there might be some missing terms because you usually truncate the expression up to first order or second order in nuclear coordinates. So you might be missing some electron-phonon multi-phonon coupling effects, which might be important at the end of the day for the temperature observable that you are interested in. So why is this methodology useful? How I like to describe it is that what cannot be resolved with this cut, and it's actually a very quick shortcut to do first principle calculations in supercells and evaluate the temperature-dependent observable of interest by just doing a DFT calculation in a big supercell with the atoms displaced. So, of course, there are some drawbacks, but also some advantages by using this methodology. The common goal of all these non-perturbative approaches, the supercell approaches, is actually to evaluate the physical property O at a particular temperature T. And here I just write the thermal average, expand the thermal average as a trace over a complete set of the eigenstates of the Hamiltonian, which are weighted by the standard Boltzmann factor. If we replace, for example, the observable with the transition rate from an electronic state alpha to a final electronic state beta and expand the trace, we can write it as a summation over the initial nuclear states. And here we again use the standard Boltzmann factor at temperature T and set is a partition function. So all these non-perturbative approaches are essentially attempting to evaluate this equation here. One can use, for example, path integral molecular dynamics, which are actually very sophisticated methods relying on the Feynman's path integral representation of quantum mechanics. But these methodologies are quite expensive, and they have been applied only for the case of a few of small molecules. Other approaches include ab-initio molecular dynamics, basically. But here the main drawback is that we miss information about the quantum nature of the nuclei, so we are not including quantum effects in our calculations, and these are particularly important at low temperatures. Other more sophisticated methodologies include path integral for the nuclei, but quantum Monte Carlo for electrons. So these methodologies are very expensive, but very accurate and have been applied only for the case of a few molecules. And then we can get a significant speed up by using importance sampling Monte Carlo. In these methodologies, the importance sampling Monte Carlo, as long as we have calculated the phonons, we can generate thermally displaced configurations for free, essentially, by relying on a multivariate Gaussian distribution. And for these configurations, we evaluate the temperature-dependent observable and finally take the average. With the special displacement method, we don't really need to generate stochastically the configurations, but we generate only one configuration and we evaluate for that particular superset size, the temperature-dependent observable. Other approaches include like performing finite differences. So we just displace the nuclei along each phonon mode separately, and then we sum the contribution to the temperature-dependent observable, or thermal lines, which is another very efficient methodology to apply importance sampling Monte Carlo. So, in principle, all non-perturbative approaches can be upgraded to evaluate any property, which can be written as a Fermi-Golden rule. This could be, for example, temperature-dependent band structures, phonon-assisted optical spectra. Here I include also like indirect gap materials or direct gap materials. One can do phonon-assisted tunneling or evaluate temperature-dependent transport coefficients. So what is the first thing that we need to do to apply these methodologies is to evaluate the phonons. And we rely first on the harmonic approximation, and we expand the potential energy surface up to second order in nuclear coordinates. So the linear term goes away because the linear order derivatives, the forces acting on the atoms at static equilibrium, they should be zero. So we want to evaluate this expression here for obtaining information about our phonons. So this information, the second order derivatives of the potential energy surface with respect to nuclear coordinates are called essentially interatomic force constants, and they can be computed from density functional perturbation theory or finite differences. After we obtain information about the interatomic force constants, we can use Fourier transformation and interpolation to obtain the dynamical matrix for a particular phonon wave vector Q, and then we can diagonalize the dynamical matrix and obtain information about the phonon polarization vectors and the phonon frequencies. For polar materials where the atoms have a different electronegativity, for example, we have to include a long-range effect coming from the dipole-dipole interaction, and this is the expression that can be included analytically as we are approaching the gamma point. So the electrophonon matrix element depends on the phonons, but also depends on the electronic states, obviously. So the electrophonon matrix elements will depend on the linear order variations of the potential energy surface with respect to a particular phonon mode, which couples the electronic state at K and K plus Q. So the perturbative approaches are actually computing this term explicitly, and they incorporate it in perturbative expressions for evaluating temperature-dependent properties. Here, for example, I use the case of phonon-assisted optical absorption in silicon. So if we want to do indirect transition and evaluate the phonon-assisted optical absorption in silicon, we need to calculate the electrophonon matrix elements. So we have an electron at the valence band maximum, which absorbs a photon to make a direct transition. In order to go to the conduction band minimum in an indirect gap material, needs to couple with a phonon. And this is actually the electrophonon coupling effect. The phonon-assisted transition rate, the theory, has been developed by Holbartin and Black back in the 50s. And this is actually the expression which says basically inside the square modulus, it says that basically these two terms, they describe the two possible paths that an electron can follow to complete an indirect transition. P is for the optical transition, and G is the electrophonon matrix elements. In the denominator, we have the Kohn-Sham eigenstates of the unperturbed system, and the delta function here is used to ensure energy conservation. So this equation has been implemented from first principles in 2012, has been demonstrated successfully to reveal the correct indirect optical absorption of silicon as calculated experimentally. But however, the only semi-empirical thing that has been introduced here is to shift the optical spectra to match the correct experimental absorption onset. And this is because if you check the delta function here, the energies of the electrons, they do not have any temperature dependence. So basically, we are missing the temperature dependence of the band structure here. A consistent theory for evaluating temperature-dependent band structures is the Allen-Heine theory. So in this theory, we need to evaluate the Van Migdal self-energy term and the Debye-Waller self-energy term in order to incorporate corrections in our calculation for the temperature-dependent band structures. So this expression is quite popular in the literature and has been implemented in several papers, which I list a few here. And if we account for this energy renormalization and apply it for the case of silicon here, you will see that the conduction band bottom lowers in energy, while the valence band maximum goes higher in energy. If we think in terms of optical absorption, this band gap closing will lead exactly to the redshift of the absorption onset. Here I also include the case of gallium arsenide, so going from 0 Kelvin, where even at 0 Kelvin have the effect of 0-point normalization, which is 32 milli-electron volts in this system. And if we go even to higher temperatures, we'll see that the band gap closing is even more prominent. So a consistent theory that can include the effect of indirect optical absorption and at the same time capture temperature-dependent band structures is the William-Lux theory. And the starting point of the William-Lux theory is the Herzberg-Teller rate, where basically we can have a summation overall final nuclear wave functions. Here P represents electronic transitions from an initial state alpha to a final state beta, and the delta function here contains the energies of the joint electron nuclear system. So if we use a semi-classical approximation and replace these joint electron nuclear energies with the adiabatic potential energy surface and neglect some commutators of the kinetic energy operator, we can get finally, and employ also the harmonic approximation, we can get finally a very nice expression for evaluating the dielectric function at a particular temperature T. So in this expression, we can essentially write it as a product of Gaussians, and the product grades overall phonon modes. And we need to evaluate the dielectric function for a particular configuration, which is generated by this multivariate Gaussian distribution. Here, the widths of the Gaussians are given by this sigma, the mean square displacement of the atoms along a particular phonon mode. And for simplicity, we use the independent particle approximation to describe the optical absorption. So the interpretation of this Williams-Lux semi-classical expression is that we need to evaluate the spectra as a weighted average with the nuclei fixed in a variety of configurations. So we generate configurations from this multivariate Gaussian distribution, and then we calculate the spectra for each configuration, and finally we take the average. So we use this concept coming from the Williams-Lux theory, and we calculate the optical absorption spectra of silicon. Here we show the experimental absorption coefficient in our calculations without using the display structure, but using only the structure at equilibrium. And we see that we are missing the indirect optical absorption, and we just have an absorption onset at the direct gap of silicon. However, if we include with the important sampling Monte Carlo electron-phonon coupling effects, we see that we capture correctly the experimental absorption onset and also the oscillator strengths for higher energies. Of course, here we are underestimating experiment because we are not including excitonic effects in our calculations. But of course, someone can combine this methodology with excitonic effects and also capture the missing oscillator strengths here. So here we have used, for this calculation, we have used about 10 configurations. And what we have found is that as we are increasing the supercell size, we found that we need less and less configurations to obtain the average spectrum, a converged result. So here is the result for 6 configurations at 300 Kelvin. And we found that even one configuration can do the job. So we were very excited about this fact. And we said, okay, can we do the maths and find out what's happening? And how can we propose a single configuration for our calculation? And in fact, if we do the exact Williams-Lux electric function and take the Taylor expansion with respect to normal coordinates and perform the integration here, we result to this expression here. If we use only one configuration and displace the atoms along all phonon modes with normal coordinates given by this sigma, we'll have this expression. So what is the error here is basically, if we compare the two expressions, is this cross-coupling terms between nu and mu. So we want basically to kill the error coming from these cross-coupling terms to get this expression here. The trivial choice is to put all the phonon modes energetically ordered and alternate the signs between the energetically ordered phonon modes between plus and minus. So these cross-coupling terms, they kill each other. And in fact, if we do that, we can prove that our choice of the special displacements will lead to the exact Williams-Lux electric function at temperature T. And here is basically the expression that we first implemented for generating special displacements. So we have applied this concept for evaluating the indirect optical absorption of silicon and diamond. And in both cases, we see excellent agreement with experiment, capturing the correct absorption onset. So here a few remarks about these non-perturbative methods and the special displacement. So these coefficients here, these second order coefficients here, basically, which are computed in supercell calculations, we can prove that they will lead precisely to the perturbative expressions that are currently used in perturbative codes. So here, this second order derivative of the dielectric function will lead to the expression for indirect optical absorption, and for temperature-dependent band structures, these second order coefficients will lead precisely to the Allen-Heine theory. So the non-perturbative methods has some drawbacks because they rely on the adiabatic approximation. They miss the phonon energies in the denominators and the delta functions. And this approximation might be okay for band gaps, which are quite large, when the phonon frequency is much smaller than the band gap, essentially. However, on the positive side is that these non-perturbative methods, they capture coefficients beyond first order or second order, and they include electron multi-phonon interactions. Also, with respect to the Allen-Heine theory, we don't rely on the rigid ion approximation, and we are including off-diagonal Debye-Waller contributions. So what's the physical meaning of this methodology? Is it just a numerical trick, or does it have some important physics? So the way I like to to convey the physical meaning of the special displacement method is this example of inelastic scattering. So imagine that the beam scatters inelastically from a material, and the beam is collected from the detector. Here, what we will see is the scattering intensity. Here, I have computed the scattering intensity of black phosphorus, and I distinguish between one phonon scattering and multi-phonon scattering. The blue dots essentially represent Bragg scattering, elastic scattering, and in elastic scattering, it comes from the scattering with the phonons, which is represented by red. So if we want to compute that using the special displacement method, we just need to open our undergrad solid-state physics book and increment this structure factor basically here. So in basically this structure factor here performs a summation over all atoms in the supercell, and here we have the standard atomic structure factor, and this phase factor is the one which determines the scattering intensity. If we forget about the ZG displacements here, we'll have only elastic scattering, and we'll have only the blue dots. But by just incorporating in this expression the ZG displacements, the special displacements, we'll get also the inelastic scattering. And as we will see here, this result is actually in excellent agreement with the exact result and also with experiment. So the way I like to describe it, the special displacement, is that it will give the best collection of scatterers at thermal equilibrium that best reproduce phonon-induced inelastic scattering patterns. So some application of the special displacement method involves evaluating temperature-dependent band structures using band structure unfolding. So if we do supercell calculations, of course, our bands will be folded. So we need to unfold them to obtain information about the band structure in the fundamental Brillouin zone of the system. Here is the example of the temperature-dependent band structure at 0 Kelvin of silicon, the electron spectral function actually. Some other applications include the calculation of temperature-dependent current densities, open circuit voltage, the zero-point renormalization even beyond DFT with GW or hybrid fractionals, the bandgap renormalization not only for periodic systems but also for nanostructures. Here, the methodology has been used for computing indirect optical absorption in this perovskite system, and also to compute the phonon-assisted emission rate and investigate these phonon satellites, let's say. So also the methodology has been used for computing exciton-phonon spectra. Here is the example of 2D germanium selenide, and with the dashed line is the exciton-phonon spectra actually. And what we see here is that the oscillator strengths are redshifted, but also there is some broadening in the spectra, not captured by using the high symmetry DFT structure. And also this methodology has been used to explain exciton-phonon coupling X-ray spectra of X-ray exciton-phonon coupling spectra in hexagonal boron nitride. And we see here that by including electrophonon coupling effects, we see that we reproduce the double peak structure observed in the experiments. In addition, as I said before, the A-SDM can be applied for nanostructures, and here we did it for graphene quantum dots, and we obtained a very nice relationship about the zero-point normalization as a function of the quantum dot size. And here also using band structure unfolding, we were able to generate the temperature-dependent band structure of a graphene quantum dot. I would like to stress a point here is that when you have degeneracies in these systems, for periodic systems, for example, because when you use finite displacements, you'll have some finite size effects, and these degeneracies will be most likely lifted. So you need to actually take the average, because that would be a numerical artifact. However, for non-periodic systems, when we displace the structure along each phonon mode, we need to actually account for degenerate perturbation theory and include a correction in the Allen-Eine theory that accounts for this degeneracy splitting. So now how can we explore harmonicity using the special displacement method? So if we have a harmonic potential energy surface, then so far what I have described is actually valid. But if we go for an harmonic case or a strongly anharmonic case, the special displacement method will collapse. However, we can update our phonons using either current state-of-the-art methodologies like the TDEP or the SHA or perturbative approaches which are basically all these approaches are described in these references here, or we can actually apply the special displacement method, because the special displacement method and these approaches here are actually brothers and sisters. I mean, they just evaluate the same thing, but with a different observable. So how can we update the special displacement method? So if we apply, we are looking actually for finding an effective potential that can capture the exact solution of the nuclear Schrödinger equation. So if we have a harmonic potential, the effective potential will actually correspond to a parabola, and it's easy to find. However, if we have this double well potential, for example, we need to do it self-consistently and find an effective potential that will give the exact solution of the Schrödinger nuclear equation. However, if we apply a harmonic approximation at the local maximum here, we see that the harmonic approximation will completely break down. Of course, we can actually do a harmonic approximation at the minimum of the potential energy surface and obtain harmonic phonons, but we have no information how these harmonic phonons, whether these harmonic phonons are accurate enough. So what I would like to describe this basically harmonic approximation at the local maximum and the local minimum is basically when you use a monomorphic structure, this will describe basically a maximum in the potential energy surface. However, if we relax the structure and obtain a locally disordered network, we can obtain a polymorphous structure, which actually represents the ground state of the system. And I just adapted the terminology monomorphous polymorphous from the famous work of Alex Zunger about the polymorphous nature of metal halide perovskites. So why do we need to get to this point to compute the phonons? I will demonstrate that this is very important point to compute anharmonic phonons with the special displacement method. So in the special displacement method, what we do is that basically we want to evaluate the temperature-dependent interatomic force constants, which are given as a thermal average of the second order derivative of the potential energy surface with respect to the atomic coordinates. And we simply replace this thermal average by the ZG coordinates basically in the system. So we just displace our system along the phonon modes based on the special displacement method, and we compute by using finite differences the phonons of the system, but now on a thermally displaced structure. And we do that iteratively until we obtain self-consistency. So the first step is to compute the harmonic phonons of the polymorphous structure using finite differences, and then enforce the symmetries and obtain an initial set of phonon frequencies and phonon polarization vectors. So here I show the harmonic phonons of the polymorphous structure of strontium titanite after I apply the symmetries. What we see here is that we have obtained stable phonons, but now our phonons, they have no temperature dependence. But this is a good starting point because the self-consistent phonon theory is designed to work only for positive definite interatomic force constants. Then we generate the special displacements using this initial set, and then we compute interatomic force constants at finite temperatures using finite differences with the ZG configuration. Then we enforce the crystal symmetries, and we calculate temperature-dependent phonon frequencies and phonon polarization vectors. And we repeat these three steps. Actually, the methodology is quite simple until we obtain self-consistency in our phonon polarization vectors and phonon frequencies. And here we also apply some iterative mixing, which is found to speed up the process by a large factor, actually, between the different iterations. And here is actually the demonstration of the anharmonic special displacement method. We have the phonons of the monomorphous structure, which are actually imaginary, and here are represented by negative phonon frequencies. Then we obtain the phonons of the polymorphous structure, which are positive definite. And starting from here, generating special displacements and basically ZG configurations, we computed the temperature-dependent phonon spectrum of cesium lead bromide at 430 Kelvin. And we see that even like the first iteration, so that's why the methodology is very efficient, even the first iteration will give a very accurate result, basically close to the converged result. And then here is the validation of the methodology compared to other approaches, TDEB or SHA or the perturbative approach by Tatano. And here what we have here is basically if we compute the phonon frequency renormalization of strontium titanite as a function of temperature for the TO modes, we see that we capture precisely the correct trends, and we have perfect agreement with other methodologies, even if we use the tetragonal or the cubic phase of strontium titanite. So what is the effect of local disorder now in metal halide perovskites, and how we can combine anharmonicity and electron-phonon calculations to compute basically the temperature-dependent band gaps in these fancy systems. So as we said before, we have a monomorphous structure, which represents the local maximum in the potential energy surface, and a polymorphous structure. So we use the polymorphous locally disordered structure. We see that the electron-phonon matrix elements will be affected both for the wave functions and also when we take the derivative with respect to the potential energy surface, this will be a different point basically in the potential. So all these quantities that entering the electron-phonon matrix elements are actually renormalized, and we would expect a different result if we use this locally disordered structure. So based on the Allen-Heine theory and basically on the special displacement method, we have computed the band gap renormalization as a function of temperature for strontium titanite and cesium lead bromide. And we see that in both cases, basically in strontium titanite, we are underestimating the band gap renormalization, while in cesium lead bromide, we are overestimating the band gap renormalization with respect to experiment. However, if we start our calculations from the polymorphous structure and displace the atoms using the special displacement method, but now starting from the polymorphous structure, we see that we get excellent agreement with experiment. And we can explain this, in particular for cesium lead bromide, we can explain the slow variation of the band gap with temperature in this system. So why is it successful? It's basically if we use the locally disordered network, which is actually the ground state of the cubic phase, is that the short-lived electrons, we have different time scales than the nuclei. We'll mostly see the nuclei in their most probable ground state configuration. And this actually calls for revisiting some open questions regarding temperature-dependent observables in perovskites, actually. So another point that highlights the importance of using locally disordered networks in perovskites is basically going from one phase, the tetragonal phase, to the cubic phase. So if we use a high symmetry network, we see that we'll have a jump and a discontinuity in the calculation of the band gap as a function of temperature. However, if we use a locally disordered network, we capture precisely the smooth variation of the band gap with temperature from the tetragonal phase to the cubic phase. So what is happening here, if we plot the potential energy surface of the cubic, the tetragonal, and the orthorhombic structure, if we consider only locally disordered structures and these minima here, the energy barrier that from going to the tetragonal phase to the cubic phase is much more smaller if we consider locally disordered networks than using monomorphous networks. And that's why basically we can actually capture this smooth variation of the band gap between the tetragonal phase and the cubic phase in cesium lead bromide. So here is the take-home messages from my talk. The harmonic special displacement method is actually a very simple and efficient methodology that even at the PhD level, you can just read the theory and implement it by yourself, actually. It's not a numerical trick. As I have shown, it has some important physics. For example, it can reproduce precisely inelastic scattering patterns. And in addition, there is a lot of space for improving these methodologies, and we can actually upgrade these methodologies for computing mobilities, conductivities, or exciton-phonon spectra, or any other temperature-dependent observable that can be written as a Fermi-Golden rule. If you are interested about this methodology and you like to use the code, you can just go to the APW website and find some tutorials about using the code. The tutorials are quite straightforward and include 6 examples about band structures, anharmonicity, and diffuse scattering. So yeah, and final point is that local disorder in perovskites plays an important role, and it's crucial for studying basically anharmonic electron-phonon properties in these systems. Finally, I would like to thank basically my Marie Curie funding, my Marie Curie fellowship at INSAREN, and also the supercomputing hours taken from TAG or PRAISE. And also, I would like to thank you for your attention.
Thank you very much, Marius, for this nice presentation. So now there's time for questions. So if you have a question, please raise your hand in the reaction section. so maybe I can start. So yeah, so if I understood also the special displacement method. So when you discussed in the beginning that one should consider more than one configuration, and then you showed that if you actually increase the size of the supercell, you can reduce the number of configurations that you need to include the temperature effects, even going down to 1. But then it seems in the end that that in some more special cases where you don't have this harmonic-like potentials, that then you need again to use more configurations. Do you understand that correctly?
Oh yeah. So basically, yeah. So basically, the point here is that when you have the harmonic approximation and well-defined phonons, you can just use a single configuration generated by these phonons with the equation I have described for the special displacement method. But when we have anharmonicity in the system, it's inevitably we need to use a few more configurations. And actually, it can be, in principle, it can be 2 configurations or 3 configurations, as I demonstrate here. So what we do here is that if we have anharmonicity in the system and we want to describe this effective temperature-dependent potential, all right, we need first to compute the polymorphic structure, for example, here, all right, to get some well-defined phonons, starting point. And then using these phonons, we generate only one configuration to evaluate. So if I come here in the convergence performance, to evaluate the temperature-dependent harmonic phonon dispersion, which is basically iteration 1 here is just one configuration, one special displacement configuration, you see? So after you obtain the harmonic phonons from iteration 1, okay, if you want to do a few more iterations, that's absolutely okay. But even if you get from this iteration 1 the harmonic phonons, then you can do harmonic electrophonon coupling calculations using, again, only one configuration. Okay. So basically the message here is just you don't really need, you simplify your sampling of your configuration of sampling. Basically, you simplify and you basically reduce the computational cost by a large factor. Of course, if you use at the end of the day 2, 3 configurations to capture the anharmonicity, that's still absolutely a great speed up.
And so how big are your supercells typically that you
based on my experience for anharmonicity here, I use a 222 supercell for cesium-lead bromide, right? So this is quite efficient to capture the anharmonicity in this system because it's a very small supercell size. But for the electrophono coupling, you need to go, basically you need to start, let's say, from a 333 supercell at least, and need to gradually increase your supercell size to obtain convergence. If you cannot increase your supercell size, and the best you can do is a 444, for example, you need, to perform the calculation for that particular supercell size, and maybe, take an antithetic configuration, which is basically a configuration with the reverse sign for the phonon modes, to see exactly what is the level of error that you have in your calculation. If these two guys, they are close to each other, which you can just simply take the average and just get a final result, which I think will be accurate enough.
You mean that those 2 configurations are very different, and so if they give a similar result,
these 2 configurations are not very different. They rely on the same phonon modes and the same mean square displacement of the atoms, but they just have different signs. Okay, so it's basically they represent so if you have displaced your atoms along a particular phonon direction, then the other configuration will be along exactly the opposite direction. All right, and then you just need to do the calculation for these 2 configurations just to test your accuracy, basically.
Okay. And maybe could you just go, you had one slide where I think you show the comparison at the beginning, I don't know, around slide 20, where you indeed used several configurations and then only one. Yeah, a bit later, I think. Yeah, oh yeah, here. So here,
So here it's not, so here the red line is one configuration and the blue dash line is just without including, so just keeping the atoms at their high equilibrium position. So it's basically using, if I use this structure, for example, for silicon without any thermal displacements, you'll get an absorption onset at the direct gap because we are not including any electron-phonon coupling effects, all right? But if you displace your structure along all phonon modes, you are incorporating the effect of electron-phonon coupling, and you can reveal indirect optical absorption.
Yeah, I was just wondering why the comparison with the experiment on the left was better than on the right, or is it?
Sorry?
What? So the comparison on the left with experiment seems to be better than on the right. Oh, but they're two different systems. Okay, that's why I lost it. Okay, they're silicon and carbon. Okay, okay, they look so similar. Okay, okay, that makes sense. Are there any questions? I don't see any raised hands. I don't know if somebody just wants to unmute and ask a question.
Hello?
Hello. Hey, Gabriel.
Hello. I have a question I should probably feel ashamed to ask, and indeed I am, but I do it anyway. I have missed how do you define your special displacement? So this can be written linear combination of atomic displacement, linear combination of normal modes. So if you could kindly repeat this. Thanks.
So basically, it's this expression is basically the normal coordinate transformation expression, all right? But for the normal coordinates, so if you have normal coordinates x, q, n, where q is a phonon wave vector and n is a phonon branching index,
Oh.
so you just replace this x with the mean square displacement of the atoms along a particular phonon mode. And this comes basically from a theory, from the Williams-Lux theory. Because if you go here to the Williams-Lux theory, so in this Williams-Lux theory, you have this integral of this dielectric function, and the integral, the Gaussians are defined, the widths of the Gaussians are defined by this sigma. And basically from this equation, we are inspired to set basically the normal coordinates of this equation here equal to sigma, all right? And then the only freedom after we apply a smooth Berry connection between our phonon polarization vectors, the only freedom we have to generate these special displacement methods is this S here, the signs basically of the phonon modes. And we have demonstrated in this paper here that there is a function that we can minimize based on this choice of signs that will lead to the non-perturbative error down to 0. All right, or at least it will minimize the non-perturbative error based on this choice of signs. All right, and this is how actually by just doing some combinatorics from the signs using the code we have basically entered the quantum espresso, will minimize the error and will generate basically these displacements, these ZG displacements.
Thanks. So you mix them according to the classical thermal amplitude, and then you have these signs that minimize the error.
Exactly.
Thanks.
Okay, thank you for the question. Any other questions? I don't see any, so maybe this is a good time to stop. So thanks again, Marius, for the nice seminar. Thanks everybody for the discussion.
It was
Merry Christmas.
Merry Christmas, yes.